In this video, we're going to cover activity 216, step-by-step truss calculations, and we're going to be looking at number 4. So here is the truss structure that has been drawn. So we have a pin connection here, we have a roller connection, 3 joints, A, B, and C, 3 members, and we have some distances labeled as well as a 50-pound force identified acting in the negative Y direction at point C. As we take a look, we're going to follow the 5-step process that is outlined in the example document that I've provided. So the 5 steps, first step is going to be to draw a free body diagram of the entire truss structure. So in this case, I'm going to go ahead and I'm going to redraw the structure. And in this diagram, we will have the forces from the supports. So in this case, the pin support, since this force is going to pull down, if you kind of imagine this force when it pulls down, if this is fastened up against the side of a building, so that's what these kind of supports are recognizing, the pin is trying to hold the truss structure onto the building. So actually the reaction that it's going to be, that joint is going to feel, is that pulling to the left. And it's also going to be supporting in the Y direction. So it is trying to hold the truss structure up as it's trying to counteract the downward 50 pounds. Since this is letter B for our joint, this is going to be known as RBX. So the arrow moving to the left, reaction at B in the X direction. The upward arrow is going to be known as RBY, reaction at B in the Y direction. Now the roller in this case allows a little bit of flexure, but the other thing too is the roller is providing one support reaction, and what it is doing is it is keeping this truss structure away from, that way joint A doesn't fall into the side of the building or fall into the side of a wall. And so you're going to see this arrow is going to go in this direction. This will be RAX, reaction at A in the X direction. And then we go through it and we're going to start taking a look at, I'm also going to label some of the distances. Now here, I'm just going to kind of label these along. I'm not going to necessarily put the dimension and extension lines in there, but I'm going to note those particular ones. This has all of our forces, but we want to solve for any forces, angles, distances that we may not know. The one thing that we will need to know is, what is this angle right here, theta? We know this is going to be 90 degrees, but what can we go through and do that? So in order to solve for this, I'm going to have to use some trig to do that. Since I know the opposite from this angle, I know the opposite side, I know the adjacent side lengths. I don't know the length of the hypotenuse. Could I calculate it? Sure, but I already know 2 of the sides of the triangle. And if I use tangent of theta is equal to opposite over the adjacent side of the triangle, and start to substitute in 3 feet over 3 feet. When I go through and in order to get theta by itself, I have to take the inverse tangent. So that way those will cancel. And the inverse tangent of 3 over 3, when I run this in the calculator, I will see second tangent, 3 divided by 3, so that gives me the inverse tangent. And then I can go through and hit enter, which is going to give me 45 degrees. Making sure that my angle is set up, or my calculator set up in degrees. Okay, so this completes step 1. Here we can put, this is 45 degrees, and we can label that in our diagram. So step 1 is complete at this point. Now we can go ahead and we can take a look at step 2. Step 2 is known as sum the moments. And as we look at the moments that are going to act on this truss structure, so we're looking at point of rotation. The point of rotation, you always want to use your pinned connection. So that is where you're going to get your rotation that could potentially happen, or your pivot point. So I'm going to take my finger and I'm going to put it on that point. Now the thing is if I take it on point C and if I pull down with 50 pounds, you notice you're going to get rotation here. Okay, this truss structure is going to want to spin around this position and cause rotation. So the question is what moments do I have to go through and experience that? So my equation here, sum of the moments add up to equal 0. And just as a little note, moments are calculated by taking force times distance. So in this scenario, I need to look at what kind of force do I have. Here I've got 50 pounds acting down, and how far away is it from, and it's the distance that's perpendicular to the point of rotation. So 50 pounds, and it is 3 feet away, and that perpendicular distance is 3 feet away from where your pin is at. So when I take a look at that, 50 pounds is acting downward. I'm going to note that. I'm going to note that as a negative 50 pounds. And I'm going to be multiplying that times 3 feet. Okay, as I go along, another force that would go through and cause rotation is the force from the roller support pushing on this side. So if I go through and if I push on this side, it's going to cause the truss structure now to rotate in the opposite direction. So it's going to be there to help counteract the rotation, the moment, generated by the 50 pounds that is acting downward. So sum of the moments, I say plus, RAX is going to the right, so that force is going to be positive. And then how far is it away from the pin? Again, the perpendicular distance to the pin is 3 feet. And I multiply times 3 feet. Those are the only types. You could say that we got another force here, but since this is our pivot point, we're going to think about that as like the 0 mark on a ruler. The edge of the ruler or the edge of the yardstick that we used in a previous activity. So any force that we have multiplied at this point is going to be multiplied by a 0 distance, which is going to cancel out. So in this case, I can go through and I can kind of ignore it. But here I've only got those 2 force arrows that are causing that rotation. So that means when I add those together, that should add up to equal 0. From here I can go through and do some simplification. So as I take a look, going across, I go through and I'm going to have negative 50 times 3 will give me a negative 150. At this point I'm going to start to kind of leave off some of the units because I think it gets a little bit heavy. However, just to show you how this works out, this is going to be in pound-feet as for a moment, plus RAX times 3 feet is equal to 0. I'm just going to tell you in some of these points in the video, I'll probably be leaving off units, just so that way it kind of, I can kind of condense this down a little bit more. All right, in order to go through and to get what I need to solve for RAX, I'm going to add 150 pound-feet over to each side to balance the equation. This will cancel. So now I'm left with RAX times 3 feet, which is equal to a positive 150 pound-feet. And then I'm going to divide by 3 feet in this case on each side, because you're multiplying. Cancels the 3. RAX is equal to 150 divided by 3 will give you 50, and of course the feet are going to cancel each other to give you 50 pounds. Alright, so step 2 is complete. We can go ahead and we can label, I can go ahead and put 50 pounds here for RAX, so that's how much force is being pushed on or being exerted by the roller onto joint A. Step 3 is what I call sum the Y forces. And very similar like what we were looking at, I'm going to take a formula. Sum of the forces in the Y direction are going to add up to equal 0. And here on my free body diagram, I need to look at what are all the arrows that are pointing in the Y direction. So the one that definitely points out to here is the negative 50 pounds acting downward. The only other arrow that I have moving in the Y direction is RBY, and it is moving in the upward direction, meaning it's going to be positive. So plus RBY, And when I add those together, that should equal 0. So to balance out the equation and to put us into equilibrium. So in order to go through and get RBY by itself, all I have to do is add 50 pounds to each side. This will cancel. RBY is going to be equal to a positive 50 pounds. And we've gone through and solved for our reaction force in the y direction for the pin. Okay, the next one, I'm going to kind of slide down here for a second. Step 4 is called sum the x forces. And very similar like how we did with with our y direction, I'm going to take the sum of the forces in the x direction, and when I add them up, they're going to equal to 0. So I'm going to start looking at what are my x direction forces. On my free body diagram, I'm going to look at, I have an arrow going left, I have an arrow going to the right, and that's it. So in this case, we do want to assume that these are both going to be positive. So RBX plus RAX, and when we add those up, they equal to 0. RBX is what we're going to be solving for. We already know what RAX is because we just solved for this in step 2. So plus 50 pounds, which is equal to 0. When I go through and I subtract 50 pounds to get RBX by itself, RBX is going to be a negative 50 pounds. Now the one thing to note is this is not a negated weight or a negated force necessarily. What this is the negative is just indicating the direction. So when you go up here, it's still going to be 50 pounds for RBX, but the arrow's moving to the left, which is noted by our negative value there. And that's kind of what follows for our forces. All right, at this point, I'm going to stop the video. This is going to be the end of part 1 for this truss structure. We're going to move into step number 5, which is called method of the joints next. And we're going to look at solving for the individual truss members that show up. What are the forces that each of the individual truss members, these 3 truss members, are going to experience in this particular situation.